In today's video, we are going to explore how sound waves are able to travel through different types of materials and how this fascinating process allows us as humans to perceive and interpret sound. To begin with, sound waves are actually nothing more than vibrations that pass through the molecules present in a medium, whether that medium is a solid, a liquid, or a gas. Since sound waves fall under the category of longitudinal waves, they move in a particular way known as a series of compressions and rarefactions. Compressions are the areas where the vibrating particles are packed very closely together, making them appear bunched up, whereas rarefactions are the regions between those compressions where the particles are more spread out and furthest apart from one another. This alternating pattern is what gives longitudinal waves their distinctive structure. Now, it may sound a little strange, but when sound waves move through a solid material, they do so by making the particles inside the solid vibrate. These vibrating particles then transfer the vibrations to neighboring particles by colliding with them, causing a chain reaction. This continuous transfer of energy is how the sound wave manages to move through the solid. Because sound waves require particles in order to propagate, the more tightly those particles are packed together, the faster the sound wave can travel. That is why sound travels much more quickly in solids compared to liquids, and even more slowly in gases, where the particles are much further apart. This also explains why sound cannot travel at all through a vacuum, since a vacuum contains no particles to transmit the vibrations. An essential point to understand is that when sound waves pass from one medium to another and either speed up or slow down due to the differences in density, their frequency remains completely unchanged. This concept is important because when we refer to the equation that defines the relationship between wave speed, frequency, and wavelength, which is speed equals frequency multiplied by wavelength, we can deduce something very valuable. If the speed of the sound wave increases as it enters a denser medium like a solid, and the frequency remains the same, then the wavelength must increase to compensate. Therefore, we can conclude that the wavelength becomes longer in higher density materials where the sound travels faster, and it becomes shorter in lower density materials such as air, where the sound wave slows down. This change in speed as sound waves pass between different materials means that sound can actually be refracted, just like light bends when it changes medium. Furthermore, sound can also be reflected and absorbed depending on the nature of the surface it encounters. Hard, flat surfaces tend to reflect most of the sound waves that strike them, and this reflection is what creates echoes, which we often hear when we shout in a large empty room or a canyon. Now, let us look at how human hearing works. When we examine the structure of the ear, we see several key components that play important roles in processing sound. These include the ear canal, the eardrum, a set of three tiny bones known as the ossicles, the semicircular canals, the cochlea, and finally the auditory nerve. When sound waves reach your ear, they travel down the ear canal and hit the eardrum, causing it to vibrate in response. If we take a closer look, we find that these vibrations are then passed through the ossicles, which amplify the sound and send it through the semicircular canals and into the cochlea. The cochlea, which is a spiral-shaped organ, plays a crucial role because it transforms these mechanical vibrations into electrical signals. These signals are then carried by the auditory nerve directly to your brain, where they are interpreted as specific sounds. Higher frequency sound waves are interpreted by the brain as having a higher pitch, like a scream or a whistle, while more powerful vibrations are understood as louder sounds. The final thing we need to discuss is the range of human hearing. The ability of a person to hear different frequencies is determined by the shape and size of the various structures in the ear. Generally speaking, the average human can hear frequencies between 20 Hz and 20,000 Hz, although individual differences do exist. Additionally, as people get older, their hearing range usually becomes narrower, mostly due to the natural wear and tear of the cochlea and the auditory nerve over time. This is why many older adults have difficulty hearing higher-pitched sounds. Anyway, that brings us to the end of this video. If you enjoyed the content and found it helpful in understanding how sound travels and how our hearing system works, then please consider giving us a like and subscribing to the channel, and hopefully we will see you again very soon with more useful science content.